Hello Whizzes, my name is Vivian, and in this video I will be showing how to approach and derive equations for acceleration and tension forces in pulley string situations. We will be looking at two different block systems. One where a block hangs on a string wrapped around a suspended pulley attached to a table with a block on the other end, and another one where two blocks of different mass hang from each side of the pulley. If that sounds interesting, let's hop into it. So a few key concepts to remember before we jump in. The first is Newton's second law. Newton's second law states that the sum of all the forces acting on an object is equal to its mass times its acceleration. So if we have a block of mass m and it experiences a downward gravity force equal to mg and an upward tension force, then the net force on the object, assuming that upward is our positive y direction, would be equal to the upward tension minus the downward gravity force. And that, T minus mg, is also equal to the mass times the acceleration because both of those are the net force. So we can use this relationship to figure out the acceleration given multiple forces that act on an object. The other thing is Newton's third law of equal and opposite forces. Let's say we have a table and we have two blocks on the surface. Let's call this one A and this one B. And let's say we exert a force to the right on these two blocks. So what will happen as a result of this force is the blocks will accelerate to the right. What will happen is block A is going to push to the right on block B. So A will exert a force to the right on B. Let's call that FA on B. And because block A pushes block B to the right, block B is also going to push back on block A with a force of equal magnitude but in the opposite direction. Let's call that FB on A. So block A will push block B to the right and B will push A to the left. And the magnitude of these two forces is equal. So those are two things to remember before we get into these types of problems. With those things in mind, let's get started with the situation with the pulley mounted onto a frictionless table with two blocks, one that's on the table and one that's hanging off the edge. So how do we find the acceleration of the system if we were to release block 2 from rest? Now, there are two different ways to approach this problem. One is going to be the fast or almost memorized way. And in the fast way, we're going to be looking at a driving force that acts on the blocks that makes them accelerate. So we're going to be looking at both blocks as a whole. So blocks as a whole. And what force drives the system to find the acceleration. Now, the better way to approach these problems, though, is through the slow way, which is where we're going to look at individual forces on each of the blocks. So how do we solve this problem using the fast method? How can we memorize the acceleration of this simple system? The net force on the system, or F net, is equal to ma by Newton's second law. So if we divide this by m, then we get that the acceleration must be equal to the net force divided by the mass. So in the case of these two blocks, we know that the total mass of the system must be equal to the sum of the masses of each block, which is just m1 plus m2. Now, what is F net? Now, F net is going to be the driving force that causes the acceleration. So what is that force? Which force is causing the two blocks to accelerate? What is causing M1 to accelerate to the right and M2 to accelerate downward? Well, we know that the Earth interacts with the system, so we know that a gravity force is going to act on both blocks. But we know that gravity is going to be pulling M2 downward, and that is going to be the driving force of the system, or M2G, because it's the gravity force on M2 that causes the system to accelerate. So the acceleration is just equal to the net force, M2G, divided by the total mass, or m1 plus m2. Now, if you just want your answer, then you're done. However, it is better to look at each block individually and derive for each individual force, because the net force on the system is not as simple as m2g in general. So I will be showing how to derive this equation now using each block individually. So let's analyze each block one by one as individual components. Now remember, since both blocks are attached to the same string, both of them in an ideal situation will have the same magnitude or value of acceleration, just in different directions. We know that block 1 will accelerate to the right and block 2 will accelerate downward. So let's look at the forces that act on block 1. Block 1 obviously has an interaction with the Earth, so it must have a downward gravity force acting on it equal to m1g. Now, the surface below it also exerts an upward normal force perpendicular to the surface. So it's going to exert an upward normal force called Fn. And Fn and m1g are equal, hence there's no net force in the y direction. The block does not accelerate up or down. So what is causing block 1 to accelerate? We see that the string here is pulling m1 to the right, which is the tension force. And that force causes the rightward acceleration of m1. So how do we write an equation for the net force of block 1? We know that the net force is equal to the mass times the acceleration. So that means that m1 times a, taking rightward to be our positive direction for block 1, is equal to the rightward tension force. So we're going to be solving for a positive value of a. Keep this in mind because it'll be important for block 2. We will also need to save this equation for later on. So let's move it up to the top. Now let's have a look at block 2, and this is where things get a little bit tricky. Once again, there's a gravity force acting on block 2 because the Earth interacts with block 2. So block 2 has a downward gravity force at m2g. And the string, or the tension, is now pulling upward. So now there's an upward tension force, T. And keep in mind that both of these tensions, the one from M1 and M2, are both equal. Now, it's worth noting that the acceleration is in the downward direction. So that means that the magnitude of M2G must be greater than T, because the block is accelerating downward, so the gravity force on the block must be larger than T in order to have a downward acceleration. So let's set up an equation for the net force on block 2. So we know that the net force is equal to ma. So, well, from kinematics, we usually took upward to be our positive direction. So can we say that m2a is equal to T minus m2g? Well, this equation isn't wrong per se, but the problem with using this is we're going to be substituting this tension in to here, which means that these two accelerations must be the same. However, if we set up the equation in this matter, it is not the same because, well, we defined rightward to be our positive direction for this acceleration here. So this equation implies that A is positive. However, for this equation here, if we took upward to be our positive direction, m2g is greater than T. So that means we're going to end up with m2a is equal to some negative number. And that will imply that A is negative, which we cannot use because we want the accelerations to be the same in order to solve for it. So how do we make that the case? So there's two ways to fix this. What you want to do is you want to set the positive direction of the acceleration to be in the direction that the object is accelerating in. So we know that block 2 accelerates downward, so we want to define our positive direction to actually be downward in order for our acceleration to be positive. So then what we'll end up with is m2a would be equal to, well, m2g acts downward, which is now our positive direction. So we'll end up with m2g minus t acts opposite to that positive direction, so minus t. And that will allow for this value here to be positive and the acceleration, the magnitude of the acceleration to be the same for both blocks. Another way to fix this is you can set up the equation in a generic way, and because this acceleration here is going to be negative, we can just stick a negative sign here to flip that acceleration. Both of the ways will work, and both of them will make sense. But I'm just going to be using the way here to solve the problem. So like I said before, t is the same in both cases in an ideal scenario. If you want to learn more about ideal scenarios, I will be putting more details in the comments. But anyways, let's substitute the tension here for this tension here, equal to M1A. So we'll end up with M2A is equal to M2G minus T is M1A. So how do we find the acceleration from here? Well, let's move all the terms with A to one side. So we'll add M1A to the left and the right. So we end up with M2A plus M1A is equal to M2G. Now we see that we have A's on both sides here, so we can factor A out from there, and we end up with, on the inside, M2 plus M1 is equal to M2G. Now, to get A on its own, we can divide by M2 plus M1, and then we end up with the same result. A is equal to M2G over M2 plus M1, or M1 plus M2. And this is the same result as before. Now we can verify our result using real values for the masses, which I'm going to do next. Alright, so I cleaned up some things a bit. So if, say, M1 is equal to 5 kilograms and M2 is equal to 3 kilograms, what will the acceleration of the system be, as well as the tension on either side of the string? Well, we can use the equations that we got before to obtain our result. So the acceleration will be equal to M2G over M2 plus M1, this equation here. So A is equal to, M2 is 3 kilograms, times G, which we said is 9.8 meters per second squared, and that's divided by M2 plus M1, or 3 plus 5 kilograms. And we get a result of about 3.675 meters per second squared. And this is the magnitude of the acceleration. So we can actually use this to figure out the tension acting on the system. So I'm going to move that up a bit. So let's move this up. So how do we figure out the tension on the system? Well, we can use this equation here to obtain our result. M1A is equal to T. You can also use the bottom one here, but this one would be a lot more difficult as you need to solve for T and do more work. So let's use M1A is equal to the tension. M1 is equal to 5 kilograms times the acceleration, 3.675 meters per second squared, and that's equal to the tension. So we get that the tension is equal to about 18.375 newtons, and that's the answer for our tension. And we can actually use these two values to verify that our system makes sense. So I'm going to clean up some things a bit, and then we're going to prove that this works. Okay, so for block 1, let's use the tension to verify that the acceleration of block 1 is indeed 3.675 meters per second squared. So we said that M1A is equal to T, which means that 5 times A is equal to 18.375 newtons. So if we divide by 5 here, we end up with A is indeed equal to 3.675 meters per second squared. So A here is to the right, and it's 3.675 meters per second squared as we defined it to be in the beginning. Now, what about for block 2? Let's see if the tension works for that problem too. So let's see what acceleration we get. Now, what will happen with block 2 is we have two forces that act on it this time. So we have a tension of 18.375 newtons, and our M2G is equal to, we're going to calculate that in a sec. That's going to be equal to 3 times 9.8 meters per second squared, which is about 29.4 newtons. So let's verify that this equation is correct. So M2A is equal to M2G minus T. So M2 is equal to 3 times A, and that must be equal to, well, M2G is 3 times 9.8, which we said was 29.4, and that's subtracted by T, which is 18.375 newtons. So we get that 3A is equal to, subtracting on both sides, I didn't put units for all of these, but anyway, 3A is equal to 11.025, and if you divide by 3, you'll get that A is indeed equal to 3.675 meters per second squared as well, downwards, as we define our positive direction to be. So what we basically have here is our tension is acting here at 18.375 newtons, and here we have that same tension acting upward, and then we have M2G acting downward with a magnitude of 29.4 newtons, which causes the system to move. So that's how you can prove that the tension is the same on both sides, as well as the acceleration. And that's how this type of problem works. Alright, so now let's have a look at a system where we have 2 blocks attached to a string that's wrapped around a pulley with no table involved. So how do we find the acceleration using the quick method first? Remember that F net is equal to ma by Newton's second law, and we know that the acceleration must be equal to the net force divided by the total mass of the system. So we know that the total mass is still equal to the sum of the masses of both blocks. So that's just m1 plus m2. Now, what is the net force acting on the system? So what is F net equal to? The first question is, what is the direction of the acceleration of both blocks? And looking at this diagram, we can see that it's based on whichever block is heavier, the blocks will accelerate either this way or this way, depending on which one's heavier. And we see that mass 2 is larger, so that means that the gravity force from this block here must be greater than the gravity force from M1. So M2G is greater than M1G. And as a result, what will happen is block 1 is going to accelerate upward, and block 2 will accelerate downward, or we'll have this kind of a motion here. So the driving force of the system is obviously going to be the gravity force from block 2 over here. So obviously M2G, the larger mass's weight force, is going to be the driving force of the system. But we can also see here that the gravity force from block 1, M1G, is in the opposite direction of the acceleration. We can see that, well, M1 is going to accelerate upward as a result of M2G being larger. So this gravity force is going to keep the system from accelerating. So we need to put a minus here for M1G. So M2G causes the acceleration, and M1G tries to prevent the system from accelerating. So putting these both back into our equation, we get that A is equal to F net is M2G minus M1G divided by the total mass M1 plus M2. Or we can also say A is equal to, we can pull out a G here, G M2 minus M1 over M1 plus M2. So if you're in a rush, then we're done. We have our acceleration here. But like I said before, this is not an ideal method to solve the problem. So let's analyze each block individually and figure out what forces act on each one. So how can we derive the equation for the acceleration? Let's look at each block individually like before, starting with M1. So we know that obviously we have a string here which provides an upward tension force acting on block 1 that causes it to accelerate upward, as shown in the diagram. So we're going to take upward to be our positive direction in this case, because we want our positive direction of the acceleration to be in the direction in which the object is accelerating. So we're going to take upward for block 1. So keep in mind F net equal to MA, so the net force on block 1, M1A, must be equal to the upward tension minus the downward gravity force in the opposite direction. So we're going to be saving this equation for later, as we'll be substituting t later on as well as in the first example. So let's move this over here. Now, what about for block 2? So for block 2, we have that same tension force acting upward on the block. And keep in mind that both of these tensions are still equal. In an ideal scenario where we have a massless string and pulley and we are not considering rotational inertia, these two tensions are going to be equal. Alright, so let me rewrite that. Now, how is it that block 2 accelerates downward, but block 1 accelerates up despite the tensions being the same? Well, if we look at block 1, T has to be greater than M1G in order for block 1 to have upward acceleration. So T is greater than M1G, but the drawing is not very clear here, so let me draw it a little more clearly. The gravity force on block 2 is actually greater than the tension, so M2G is greater than T, which is the reason why the block has a downward acceleration. So, like before, we're going to set our positive direction of the acceleration to be in the direction in which this block is moving, which is downward. Again, we want to have a positive magnitude of acceleration because, like before, let's write this equation in terms of downward being the positive direction. So, the net force on block 2 is equal to M2A, and that must be equal to the downward gravity force M2G minus the upward tension. And once again, we said that because M2G is greater than T, this is going to give us a positive value of the acceleration. And here, because T is greater than M1G, we're going to end up with a positive acceleration here, which is why we can use a substitution in both these cases. So how do we do the substitution? So we can actually solve for the tension in one of these equations. I'm going to do it with this one. So if we add M1G on both sides, I get that T is equal to M1A plus M1G. So we can substitute this value for the tension into this tension here. So we get that M2A is equal to M2G minus, so we're going to make all these terms negative because we have a negative sign. So we need to make all these negative. So we get minus M1A minus M1G. So putting the parentheses around, it would look like M2A is equal to M2G minus, the tension is M1A plus M1G. And when you distribute this, it will turn out like this. So now, like before, let's add all the terms with A to one side. So we need to move M1A to the left side. So we're going to add M1A on both sides. And then we end up with M2A plus M1A is equal to M2G minus M1G. Alright, so now that we have all our A terms on this side, we can actually factor out an A here. So we have A multiplied by, we're left with M2 plus M1, and that's equal to M2G minus M1G. Now, to obtain the acceleration, we just divide by this thing in parentheses here, M2 plus M1, and we end up with A is equal to M2G minus M1G over the mass of the system, M2 plus M1. So that's our answer. We obtained the same result as before. And this result makes sense because, again, the gravity force of block 2 is causing the acceleration of the system to be in this direction. But the gravity force from mass 1 prevents the system from accelerating. And using the internal force of tension, we're able to obtain this result. Alright, so now let's use some actual values for M to obtain the acceleration. So let's say that M2 is equal to 8 kilograms and M1 is equal to 2 kilograms. So how can we find the acceleration as well as the tension? So let's find the acceleration first. So we can use the equation on the right-hand side here. So the acceleration is just equal to, well, we can pull a g out because both the terms here have a g here. So we could just say 9.8 meters per second squared off the bat, multiplied by m2 minus m1, or 8 minus 2 divided by m2 plus m1, which would just be 8 plus 2 kilograms. And that gives us a result of around A is equal to 5.88 meters per second squared. So we're going to use this value to figure out the tension now. So let's move some stuff around. So I'm going to get rid of this and move this here. So now let's figure out the tension, and we can actually do this using either equation once again because the tensions are equal. I'm just going to go ahead and use this equation here. So T is equal to M1A plus M1G. So our M1 is equal to 2 kilograms. I'm not going to write units here for space. And the acceleration is 5.88 plus, and then M1 is 2 times, and then G is 9.8 meters per second squared. And that will give us an answer of T in our calculator, about 31.36 newtons for either block. So now let's see if we can use this tension and the gravity force to check if the acceleration is correct. So let's verify that the tension is the same in both strings and the acceleration in each block's respective direction is the same in magnitude. So for block 1, we said that the net force M1A was equal to the tension minus M1G. So that means M1, which is 2 times the acceleration, should be equal to the tension, which is 31.36, minus M1G, which is just 2 times 9.8 meters per second squared. So that means 2A is equal to 31.36 minus 19.6. So that's going to give us around 31.36 minus 19.6 gives us 2A is equal to 11.76, and we divide by 2 on both sides, and it gives us an acceleration of 5.88 meters per second squared in the positive direction. So our tension here is equal to 31.36, and our M1G is equal to, this is our M1G right here, 19.6 newtons. So we can see that that causes that upward acceleration, and indeed M1G is less than the tension in magnitude. Now what about for block 2? Let's verify block 2. So for block 2, we said that the net force M2A was equal to the downward gravity force minus the tension, given that downward is our positive direction. So that means that M2 is 8 times A, should be equal to the downward gravity force on block 2, which is 8 times 9.8 meters per second squared minus 31.36. So we should get an answer of A is equal to 5.88 meters per second squared. My bad. So that means A is equal to 8 times 9.8 is equal to 78.4 minus 31.36. So that means AA is equal to 78.4 minus 31.36 is equal to 47.04. We divide by 8, and lo and behold, we get an answer of 5.88 meters per second squared. So the gravity force acting on block 2 is equal to 78.4 newtons, but the upward tension T is only equal to 31.36. Hence, we have a downward acceleration of block 2, and indeed, M2G is greater than the tension. So that's how these problems can be proved, and we can see that the acceleration is the same on both sides, just in different directions. Thanks everyone for watching my video, and if you have any questions, feel free to put them in the comment section below. Have an amazing day, stay happy, and we'll see you next time. Goodbye.